I'm sorry, I'm seeing a flag here. So, oh, someone chatted something. Yes, okay, great. I don't know what it was. Well, probably you could hear me when I was saying yes, great. Thank you. I'll just leave the chat. So you can also type it in if you need to. If you're shy about using your voice to ask a question, just do it on the chat box and I will answer. I will keep your names undisclosed if you want to, although people can look at the chat box and see who it was. Okay, so now remember we talked about conjugate acids and bases, and in this table here, let me make sure that I didn't advance more than one slide. Yeah, I did advance more than one slide. Okay, so we're going to get to that table in a second. So this is a weak base, and this is the weak base dissociation. Again, a weak base, what it's going to do is going to accept a proton. So NH3, by accepting a hydrogen, is going to go to NH4, but it's not a hydrogen what it accepts. It accepts a hydrogen with a positive charge. So once it brings a hydrogen with a positive charge, then it's going to have a positive charge. So it's NH4 plus. So these are conjugate acids and bases. They differ by one H plus. So NH3 and NH4 are not conjugate acid and base because although they differ by one proton, they don't differ by plus one. The base usually will have the positive charge. Now they're conjugate acids and bases. This will be conjugate. Okay. Okay, so let me erase that. Doesn't make sense to have it there. Oops. What's the matter? Yeah, it should be erasing. Okay. Okay, great. So this is, and the other conjugate acid and base is going to be, let me change colors, H2O and OH minus. Again, they differ by one hydrogen plus. So if I go this way and add a hydrogen plus to the OH, I will form H2O. So now for H2O, we have three. We have OH minus, which is the conjugate base of H2O. And the H2O, the conjugate base of H2O is OH minus. The conjugate acid of OH minus is H2O. But H2O can be the base because it can accept a proton because it has lone pairs and form the hydronium ion. So this is an acid-base pair. This is an acid-base pair. They differ by one H plus. Let me put H plus here and H plus here. So water actually can be, in this case, in this first case, let me switch colors again. In this first case, the water is an acid. Excuse me, not an acid, a base. Why? Because it's accepting a proton from, excuse me, no, it's an acid. You see that it gets confusing. So so in here, the H2O has accepted the OH has accepted the proton and it formed the acid. So this is the base. It's accepting a proton. And if this goes this way, then it will act as an acid. It gives off a proton and turns into OH minus. However, if we look at the next, let me switch maybe to red. We look at these two here. The H2O is accepting a proton to go to a hydronium ion. So this is a base. And the hydronium ion will be the acid. I know it can be confusing if you have not thought much about this one. Just take the notes that I just have, and before I erase them, before I switch to the next slide. Okay, so for weak bases, what you have is, again, is reacting. All of them are reacting with water. So let's look at ammonia, the very first one. So ammonia is reacting with water, and the water is acting as an acid. It's going to give the H plus to NH3 and form NH4. And what is going to be left of the water once it releases the H plus is going to be OH minus, or the hydroxide ion. Okay, so again, you have acid-base pairs. So let's look at them again here. And so I'm going to probably erase this one here. Maybe I'll erase these ones here and use different colors. So this is going to accept a proton from the NH3, is accepting a proton from water, and therefore is going to be the base. Let me write it up here. Base. I apologize for the lack of contrast there. And its conjugate is going to be the acid, and the acid will have one more H plus, which will be NH4. So that'll be the conjugate acid. If we look at, let me switch colors. Yeah, let's do green. H2O is donating a proton, so it's acting like a base, like an acid. And once it leaves, it gives off the proton, it turns into a base, OH minus. So on acid-base equilibrium, you always have this kind of behavior. So let me use another color, red. So you have a base plus an acid turning into another base plus another acid. And they're going to be, the blue ones are conjugate one another. The green ones are conjugate of one another. Again, the conjugates means that they only differ by an H plus. Okay, so this is an acid-base reaction going forward, and going backwards is also an acid-base reaction. Which side is going to predominate at equilibrium? At equilibrium, the reactant side is predominating because of the small values, 10 to the minus 4, 10 to the minus 5, 10 to the minus 9, 10 to the minus 10, which means that they are much less than 1. So they are going to be mostly the bases themselves, the reactants, these guys here, are going to be the predominant species in solution. Okay. Okay, let me stop the, so this is what we were talking about. I will not stop right now, but I will stop it soon. So again, you have the HNO2 being the acid, and its conjugate base is going to be NO2. Again, they differ by an H plus. So you add an H plus, you're going this way. That means that the NO2 is going to accept a proton and turn into HNO2. A proton is H plus, which is really, in reality, is the hydronium ion. Okay, so the hydronium ion is the one that gives the proton, and so this is going to be in terms of water, this is the acid, and this one is the base. The acid will always, if you get confused, just look at the two, and the one that has the extra hydrogen with a positive charge is going to be the acid. So base accepts protons to form acids, and acids release protons to form their conjugate bases. So again, here you have the acid, has the extra hydrogen. Here you have the conjugate base. It's missing not only the hydrogen, but also a positive charge. So it has turned negative. When you look at these guys here, the water. So the water is going to be the base, and the hydronium ion is going to be the acid. The base will accept a proton, and yes, it's going from H2O, and the hydrogen, this hydrogen here, is going to go in there. And that's what you see, that's the product. Okay, the other reaction that is going to be important, I think this is very important, so please pay special attention, make sure that you understand that you can write it. Don't forget the AQs when you write the equation. You have ammonia and water. So they both are neutral, and both have hydrogen. So which one is going to donate the hydrogen to which is going? You have to remember both have lone pairs. This is one lone pair. The water has two lone pairs, and yet the water is the one that is going to act like an acid. And that's reflected also in the formula, because the formula here starts with H2O. The hydrogen here, the hydrogens here are not at the beginning, which is a clue that those hydrogens are not acidic. So water has the acidic hydrogens. So one of these hydrogens here is going to go and pair with the lone pair there and form NH4. So this is the base accepting protons. This is the conjugate acid, the one that has accepted the proton and has now a positive charge. Water has acted like an acid, meaning has given off the hydrogen plus, and what is left is OH minus. So this is the conjugate base. So notice that in this case, you always have a base plus an acid in equilibrium with an acid plus a base. Okay, so if we are talking about this one being the base, then this one is the conjugate acid. So we could erase this one here and say conjugate here. And that is correct. So they're really a conjugate pair. So this guy and this guy are conjugates of one another. One is an acid, one is a base. Okay, so when we look at acid-base pairs, we can look, and if you look in here, you have 4 of all the strong acids. You actually have 5 of them, although we're missing one here. And we're missing 2, HBr and HI are missing there. So out of the 6, we're missing 2, that should be 4, but notice the hydronium ion is also a strong acid. So these strong acids dissociate 100%, so you're never going to find them as dissociated ions. They're going to be, never going to find them as undissociated species. They are going to dissociate to form the conjugate bases, which are on this side here. But if you go to weak acids, then you're going to find that part of it dissociates, part of it doesn't. So among the weak acids, these are the stronger, not strong acids, but stronger weak acids. And these are the weaker weak acids. They dissociate the least. Okay. So when you look at an acid-base pair like this, let's look at this one. There's going to be, it's more like a seesaw. when you look at these acids and bases. So the seesaw can be like this. The seesaw can be towards one side, or the seesaw can be inclined toward the other way. So when you look at this scale here, you're going to find out that the weaker the acid, the stronger the base. So when you go all the way to the bottom, you have very weak, but if you come to the conjugate bases, they're going to be very strong. So you have what is called a leavening effect. As one goes up, the other one goes down, and vice versa. And that has to do with equilibrium, because you can write the equilibrium of the weak acid. Remember, most of it is going to be towards reactants. But if you flip the equation, you're writing the equilibrium of the conjugate base. And the equilibrium of the conjugate base then is going to be mostly towards products rather than reactants if you flip the equation. It's a very same equilibrium. It's just whether you view it as from one side, let's say from the left, or from the right, as being the reactant side. So let me stop here. Oops. Stop recording. Okay, so one of the last things we're going to look at today is going to be the auto-ionization of water. So water auto-ionizes. What does that mean? Water, remember, that can be a conjugate acid or conjugate base. So it can be an acid or a base, and being able to be an acid and a base at the same time, it can react, one molecule can react with another. Meaning one of the molecules are going to be the acids. They're going to be able to take one proton, take it and give it to the other molecule of water. If they do that, you're going to get a hydronium ion, and then let me see, an hydroxide ion is going to be left behind. So an OH minus, which is here. So remember that when the H plus leaves as H plus, it leaves the electron pairs behind. So this little connector here, let me change colors. This little connector here is going to remain with the OH, and that represents 2 electrons, 1 and 2. So when the hydrogen leaves as H plus, then the 2 electrons that were there, now they're going to become lone pairs. So these are the 2 electrons that were there before. So water can react by itself, with itself, and form a conjugate acid and a conjugate base, the hydronium ion and the hydroxide ion. Now, the equilibrium lies to this side, heavily. So the Ka for this is called Kw, yet another K, and the W stands for water. So, and notice that the Kw has 10 to the minus 14, a very small number, which means that most of it is going to be in this. In reality, one molecule in about 10 million molecules will, if you could look all the way into the water, 1 in 10 millions are going to be dissociated like this. But as they dissociate, they're very likely to collide back again. They have opposite charges, and they go and reform the water. So this is happening constantly throughout any aqueous solution. You'll have this equilibrium. The equilibrium of water, which is called Kw. Again, Kc will be this one. These 2 concentrations are constant, and therefore they're incorporated into the Kc. And the only thing left for the Kw is going to be the concentration of hydronium ions and the concentration of hydroxide ions. And this is an equilibrium that is going to be present in any aqueous solution. Regardless if there's any other acid-base equilibrium, this is always present. So this is always going to be true for any solution. And this is going to become very important because when you do your calculations, you need to consider this equilibrium as well when you're working in aqueous solutions. Always true for all, let me just put AQ, which denotes aqueous solution. So in pure water at 25 degrees centigrade, which is the laboratory temperature, the concentration of hydronium ions and hydroxide ions is 1.010 to the minus 7. So although the water is neutral because it contains equal amounts of acid and base, there are some hydronium ions. There are going to be some hydroxide ions, even if you have pure distilled water. Why 10 to the minus 7? Because if you remember here, the stoichiometry is 1 to 1 to 1 to 1. So the hydroxide ion and the hydronium ion are going to always be formed in a ratio of 1 to 1, which means that this will be X. If this is X, then this one will be X. So X squared is going to be 10 to the minus 14. X is going to be the square root of that, is going to be X, and X is going to be the square root of minus 14, which is going to be minus 7. So that's why we have the concentration of hydronium ions and hydroxide ions in aqueous solution are always going to be this for neutral water. Once you add an acid or a base, these concentrations are not going to be equal, because otherwise it would be remaining neutral. They don't remain neutral when you add an acid or a base to water, but this equilibrium here will be obeyed, meaning that the concentration of hydronium ions times the concentration of hydroxide ions will always be 10 to the minus 14.